Hello and welcome to the second day of Unit 4, 4.2. You'll notice that in your notes there's a warm-up. We're going to do that warm-up in class. Okay? We're going to jump straight into the lesson today. So the first two things that we need to talk about are the first and second derivative tests. Now, I'm hoping that up to this point we've sort of come to our own conclusion that the first derivative tells us something about whether the graph is increasing or decreasing, because it gives me values of the slope, and therefore whether the slope is positive or negative tells me that the original graph is increasing or decreasing. So first derivative test tells me something about increase and decrease, right? So positive first derivatives or negative first derivatives. The second derivative test tells me something about concavity. Okay, so concave up or concave down. Okay. And we're concave up when the second derivative is positive, and we're concave down when the second derivative is negative. Okay. So we're going to keep these two ideas in mind while we look at the upcoming examples. Okay, so for our first example, we are given the graph of f double prime. So this graph represents the second derivative of some function f. All right, and using that graph, I want to first state the x-coordinates of points of inflection, and then state the intervals of concavity, where it's concave up and where it's concave down. So remember, points of inflection are where the concavity changes. And since this is the graph of the second derivative, it's telling me what the concavity is. In other words, the y values are telling me whether it's concave up or concave down, being that the positive values of y say that the original graph f was concave up, and negative values of y, the original value or the original function is concave down. So points of inflection are going to happen where the graph goes from negative to positive. So at -3, at 0, and 5. So at -3, 0, and 5, the second derivative changes from either negative to positive or positive to negative. In other words, it crosses the x-axis. The reason we did not include 3 was because the second derivative did not go from negative to positive. It stayed negative. It touched the x-axis, but it didn't cross it, so the concavity did not change. Okay. All right. Now the question is, where or what interval is the function, the original function, concave up? Okay. That's going to be where the second derivative is positive. So we're concave up from 3 to 0 and negative or 5 to infinity. Okay. We are concave down where the graph is negative. So from negative infinity to -3. Ooh, and I just realized that was -3. -3 to 0. Okay. Union 0 to 3 union 3 to 5, and that's it. Now, it is interesting here we say that the graph, the original function, has no concavity, right? It has no concavity at 3. So that means it's either horizontal or vertical. That's interesting. But just take note of that. Now that's one of those things I said there are many schools of thought. My school of thought is that there is no concavity at 3. So that's how I'll be grading. Okay. The AP test, it depends. They'll give you credit for this because they understand that there are various schools of thought. So it just depends on what textbook you're using. All right, in example 2, we're going to be looking at another function, but this time we're given the graph of f prime. Okay, given the graph of f prime, can we come up with some information or answer some questions about it? So the first thing is looking at f prime, can we come up with the intervals of decrease? So remember, if this is the first derivative, it's telling us about the intervals of increase and decrease, right? That's that first derivative test. So positive values of f prime, intervals of increase. Negative values of f prime, intervals of decrease. Okay? So intervals of decrease, I'm looking for negative values of f prime. So from -3 to 0. And from 3 to 5. That's where the graph of f prime is negative, or the original function is decreasing. Okay. Okay, where am I concave up and where am I concave down? Now that's a little bit trickier of a question because remember, concavity was something that we got out of the second derivative, but we're only given the first. Well, when you find the derivative of a function, you're finding its rate of change. You're finding the values of the slopes. So just thinking about the second derivative test, concave up would mean positive values of the second derivative, or where the first derivative is increasing. So the first derivative is increasing from -2 to about 1.5. So the original function must be concave up from -2 to about 1.5. But that's not the only place the first derivative is increasing. The first derivative is also increasing from 4 to infinity. Now again, concave up, the second derivative tells me that if the second derivative is positive, I'm concave up. In order for the second derivative to be positive, the first derivative must be increasing. So that's what I was looking for, was the intervals of increase of the first derivative. That told me where the second derivative was going to be positive. Concave down, similarly to the concave up, given the first derivative, I'm looking for where the first derivative is decreasing, because that's going to tell me where the second derivative was negative. So how about from -infinity to 2, -2, and then from 1.5 to 4, right? And then POIs, points of inflection. Points of inflection are where the concavity changes from positive to negative, or changes from concave up to concave down. Well, you can sort of see here, -2 is where I'm going from concave down to concave up. And right here you can see at -2 I have a minimum of the first derivative, because that's where the first derivative changes from a negative slope to a positive slope. And that's where the second derivative changes sign. So -2. But there's another one, 1.5, changing from a positive second derivative to a negative second derivative. And there's one more, 4, changing from a negative second derivative to a positive second derivative. Okay, so you can sort of see those here. 1.5 is in both, 4 is in both. Those are the places where I'm changing concavity. Okay. Again, so first derivative tells me about the slope of the original function. The derivative of the first derivative is the second derivative, and therefore the rate of change of the first derivative is what's telling me about concavity. Okay, so for our last example, one of my favorite kinds of problems is we're going to be given a bunch of clues and we have to come up with the graph based on the information given to us. All right, so f of -1, f prime of -1 is 0. That means that the slope of the graph at -1 is horizontal. So at -1, we have a horizontal slope, wherever that is, wherever that happens to be. Oh, look at this. F of -1 is 4. So at 4, I got a horizontal slope. Okay. F prime of x is less than 0 if the absolute value of x is less than 1. Okay, let's not forget from Algebra 1 how we write these. This absolute value inequality is the same as that. So for x between -1 and 1, the slope is negative. So between -1 and 1, I'm decreasing. F prime of 1 doesn't exist. So whatever f of 1 is, 0, the slope does not exist there. Well, since the value of the function exists there, we know that it can't be discontinuous there. So what's the only thing that's not differentiable but still continuous? We'll keep that in the back of our heads. Okay, so we've sort of used that. Let's see. F prime of x is greater than 0, so the slope is positive if x is outside of 1. So remember, this is written as x less than -1 or x x is greater than 1 or x is less than -1. So outside of -1 and 1, the slope is positive. Okay. The second derivative is negative as long as x is not equal to 1. So that means I'm always concave down. Okay. So let's see. Let's put this all together. On this side of -1, I have to be increasing because the first derivative is positive. And I'm always concave down. So it's got to look something like this. Something like that. Okay. On that side of 1, okay, I've got to be increasing and concave down. So same sort of shape. And this said that between -1 and 1, I had to be decreasing, and at -1, the slope didn't exist. So that thing that is continuous but not differentiable is a cusp. Okay? And that's an idea of what the graph would look like. Now, the only points that really matter here are this one and that one, because we were given those, right? We were given those values. Everything else was sort of inferred based on the information. Okay. So what I mean is this may be out further, or maybe it doesn't. You know, maybe it's like, maybe you got it going like that. Whatever, as long as it's increasing, concave down, as long as it fits. But that works.